Hello everyone. So today is the fifth week of the course Classical Mechanics of a Single Particle, and today we will talk about the previous year assignment week 5 uh, courses and questions with answers. But before going there, I just want to focus here one thing, that in the previous class we talked about the central force field, right? And then there was Bertrand's theorem. Then there was Bennett's theorem. Bennett's theorem was also, Bennett equation was also in the previous one. But the thing is that in the previous class we were discussing about the Bertrand's theorem, and then we were talking about that repulsive, attractive and repulsive inverse square force law. But in that case, in the previous class, I just made a mistake of two questions. That's why I just want to focus these two questions, and after that we will start today's class and with 5 classes. Okay. So what are the questions? I just made a mistake a little bit, so I just want to focus here. And this was the question number 5 from the previous class. Previous week number 4. Okay, so what was the question? For a repulsive inverse square force law, which of the following are true? Okay, so repulsive inverse square force field. So I just want to focus here one thing, that what I did in the last class a little bit wrong. So that's what I just want to mention here. I'm really sorry for that wrong answer. So I want to clarify here that in that question it was mentioning that the force is a repulsive inverse square force field. Okay, so that means if R can be written as K divided by R square, and that should be a plus 1 because it is mentioning as repulsive. Okay, so this is the FR for our case. Very good. Which of the following is or are true? Okay, so if I have the FR as K by R square, then what is V of R? V of R is minus FR dr. So it will be minus K by R square dr. So it is minus of minus K by R plus C. And you can understand that at R tends to infinity, V of R is 0. So C is equals to 0. This we all know. So that means our VR is plus K by R. Okay, it is a plus K by R. Now if VR is K by R, then what is the energy conservation expression? The energy conservation expression is half m r dot square plus L square by 2m r square plus V of R equals to 0. Sorry, equals to energy. That we all know, right? And if I want to write here half m r dot square plus L square by 2m r square plus K by R equals to E. That is the thing. Now in this case, in the repulsive inverse square force law, force field, we have the V effective as L square by 2m r square plus K by R. Okay, this is my V effective. Okay, very good. Now come to the question. The trajectories are conic sections, all motions are bounded, mechanical energy is always negative, the trajectory is always circular. Okay. Now I just want to plot here the V effective versus R. Okay. So let me write here V effective. It is L square by 2m r square plus K by R. Now you can understand, if I plot V effective then R, then what will happen? As R tends to 0, our V effective will be L square by 2m r square, right? So it will be like that. Okay, and at V equals to infinity, our V effective will be K by R. And one more thing is that here in this V effective versus R, can we get any point where V effective will be 0? To get V effective as 0, we have to go somewhere as infinite value, and both are positive one. So that means we can write it like this one only. That was my mistake in the last class, that what I just showed the similar one as inverse scale law. I mean attractive inverse scale law. But if it is a repulsive inverse scale law, so that means you have to write like that. Okay, fine. Now V effective is like that. Now the trajectories are conic section. Okay, this is always true because it is a central force, as well as this is an inverse square central force. So it does not, the result of for this first question does not depend whether it is plus or minus. For all the condition, the trajectories are conic section. That is fine. All motions are bounded. Now coming here. If I want to draw one line for energy here, somewhere, and you can see that it will come as 0 at infinite. So that means it is no longer going to touch the r-axis, right? So now, if I write here, this is E, let's say E1, E2, E3, something like that. So anywhere in this plot, we can't have a bound state. It is like all the E's are positive, but we can't have a bound state. So all are unbound states. So all motions are bounded. That is not correct. Mechanical energy is always negative. No, mechanical energy is not always negative. We can see that our energy is getting positive here. And obviously we were seeing in that previous classes that if energy is positive, we can have either parabola or hyperbola, right? So these two can be possible here. So in mechanical energy is always negative, it is not correct. The trajectory is always circular. No, the trajectory will be only two possibilities there. Either it can be parabola or it can be hyperbola. It cannot be circular or ellipse. Okay, so this was the first question's answer. Now coming to the, yes, this one. This one is also from the previous week question, where also it is repulsive inverse scale force law. So for motion under repulsive inverse scale force law, so again I can write here that inverse scale force law is like Fr is K by R square. So K by R square. So Vr is again positive K by R. That trajectories are hyperbolic or parabolic conic sections, as we have already seen that for repulsive inverse square force law, and E is always greater than 0 and unbounded motion. Okay, so only parabola or hyperbola conic sections are possible. Okay, so this is the case. Now the trajectories are hyperbolic or parabolic conic section. That is correct. The total mechanical energy is positive. Yes, the total mechanical energy is positive always, because for this case it is okay. So this is also correct. Now the orbit is unbounded. Yes, the orbit is unbounded. In this condition, so we take a what will be the plot for effective potential versus R. So that one also we just did right now, that effective potential versus R will be like V effective and R, and it will be like this one. So So you can see that always all the energy values will be positive only and it will be unbounded because they are at the infinite point there will be a boundedness. That's it. Okay, so I can just write it to this one as well. Okay. So these two questions were there from the previous week, where what I thought that I have to mention here in this lecture. Now coming here for the question number 1. For this class. Okay. Okay, so for this class, basically what we will talk here, we will basically do one thing that we know. Butler's theorem told that we have a closed orbit for bounded motion if the central force field are two types. So what are the types? Obviously we all know that right now that central inverse square law and the other is harmonic oscillator. Right? So inverse square law is 1 by r square. F is proportional to 1 by r square, here proportional to r. Okay, so these two were there. Now in this bit number 5, sir was discussing about the if I have harmonic oscillator, then f of r is proportional to r. So let's say f of r is like minus kr, where k is positive. Okay. Now a simple harmonic oscillator has a mass of m 10 gram. Okay. Let me write here m x double dot equals to minus kr. Like if x I am talking, then m x double dot plus kx equals to 0. Then h double dot plus k by m x equals to 0. So I can write it again here, omega square x equals to 0, where omega square is k by m and omega is angular frequency. Okay, and k is the stiffness constant of the spring, and m is the mass of the particle. Okay, so what the question was telling, a simple harmonic oscillator has a mass of 10 gram. 10 is given as 10 gram and is attached to a spring with stiffness, that means k is given as 500 dyne per centimeter. What is the natural frequency of oscillation? Okay, so we know that omega square equals to k by m and omega is root over k by m. So k is given as 500 divided by 10, so it is like root 50. Okay, so natural frequency means 2 pi f equals to omega and f equals to omega by 2 pi. So I can write here root over 50 divided by 2 pi. That will be answer. Let me calculate here. Root over 50 divided by 2 into pi. It is 1.1255. It will be hertz because the frequency has the unit is hertz. So okay, what was the answer? 1.12. Okay, that means this 1.12 hertz. So for this, what we did, we just calculated that the mass is given here as 10 gram and the stiffness is given 500 m per centimeter, and both are given in CGS unit, so we don't need to convert anything in any another specific unit. And then the natural frequency is given as this one. So obviously we have to take care about this language, that they are asking about the natural frequency, they are not talking about the some angular frequency. Angular frequency, this is f, and if angular frequency is there, then is omega, and the natural frequency is f. So this is that is 1.12 hertz. Now coming to here, question number 2. The displacement of a harmonic oscillator is given by xt equals to a cos omega t minus phi. Okay, very good. If the initial displacement, right, if the initial displacement is 2 cm and the initial velocity is 3 cm per second, what are the amplitude and phase of the motion, and omega is given as 3/2 hertz. Okay, let me write here. Actually this should be radian per second or something. Okay, fine. The displacement of a harmonic oscillator is given by a cos omega t minus phi. Okay. Now, what are the conditions given here? The conditions are initial displacement is 2 cm. Initial displacement means at t equals to 0, x is x0, which is 2 cm. Okay. Another condition is initial velocity is 3 cm. That means at t equals to 0, v is v0, which is 3 cm per second. Omega is also given 3/2. So they are asking what will be the amplitude and phase of the motion. Okay. So how we can do that? Okay. So let me write here the equation. A cos minus yes, minus t. Okay. Now come here, as here in that case Vt was given, right? So we have to calculate V as well. So Vt is what? Vt is x dot t. So this will be like minus a sine omega t minus phi, and then 1 omega. Okay. Now at t equals to 0, x0, which is x0, is a cos minus phi. So it can be written as a cos phi simply. Okay. Now x dot 0, which is v0, this is v0, that I can write at minus a sine minus phi. Minus phi, sine minus phi is minus sine phi, so it will be a sine phi. Okay. So I can have x0, here omega is there. So a cos phi and v0 is a omega sine phi. Very good. Now if I have these two, then I can do one thing, that a square cos square phi plus a square omega square sine square phi equals to v0 square plus x0 square. And also I can do one thing, that v0 by x0 is a omega sine phi divided by a cos phi. Okay. So a will cancel out, it will be simply omega tan phi. So omega tan phi is equals to V0 by x0. Now what are the values of V0 and x0 in this case? V0 is 3, x0 is 2. 3, 2. And what is tan phi right now? 3 by 2 into 1 by omega. So what is omega? 3 by 2. Okay. 3 by 2 into 1 by 3 by 2. So you can understand that is exactly 1. That means our phi is 45 degree. Right? Okay. Now I just want to write here what is A. Okay. A can be calculated very simply. x0 A cos phi and A cos 45 degree. So cos 45 is 1 by root 2. So A will be root 2 into x0. So 2 root 2. If I calculate 2 root 2, then the value is 2.828. So I can have, that means amplitude A equals to 2.82, phase phi equals to 45. Now let me compare this with options. Okay, see, A equals to 2.828 and phi equals to 45. So this is the answer. This will not, this will not, this will not. Okay. So this is the case. Now come to question number 3. For an oscillator of amplitude A, angular frequency omega, the total mechanical energy is given by what? Total mechanical energy. Okay. So I have the total mechanical energy as half m extra square plus V of r, because this is the kinetic energy part and this is the potential energy part. Now for harmonic oscillator case, f of r is minus k into r. So what is V of r is minus integration f r dr. So it is sorry, minus k r dr. So it is k r square by 2. So I can write the total energy E as half m extra square plus half k r square. This is the kinetic energy, this is the potential energy. Okay. Now this is the total energy, total mechanical energy. Now if I have xt as A cos omega t minus 5, then extra t will be minus A sin omega t minus 5 and omega minus A omega sin omega t minus 5. So our energy will be half m extra square plus half k x square, which is half m minus A omega sin omega t minus 5 whole square plus half k A cos omega t minus phi whole square. So the answer will be half m square omega square sin square omega t minus phi plus half k square cos square omega t minus phi. Now you can understand it is like half m square omega square sin square omega t minus phi plus half k square cos square omega t minus phi. Now from this definition of omega square as k by m, so I can write it like half m square omega square is k by m sin square omega t minus phi plus half k x square square cos square omega t minus phi. Now you can see I can write it half m k square sin square omega t minus phi plus half k square. M will not be there, m will cancel out, so m will be cancelled out. Cos square omega t minus phi. So it is nothing but half k x square. So the total energy is half k square. Right? So half k square. So this is the answer. Translated of amplitude A and angular frequency omega, the total mechanical energy is given by R. In this case, we can see we have written all the total energy terms in terms of omega amplitude and angular frequency omega with the help of the expression that omega equals to k by m into p. Okay. Now let me go for the fourth question. The area of an ellipse traced by a harmonic oscillator in phase space with momentum is what? Okay. So how do we do that? Area for an ellipse is nothing but pi a b, where a is semi major axis, b is semi minor axis, right? So they are asking that what will be the area of the ellipse traced by an oscillator in phase space with momentum is. Okay, in phase space with momentum. That means I can have a plot like that, phase space with momentum. Phase space with momentum means here it is x, or let's say here it is x, and this is amx dot. This is the momentum, right? So x with amx dot. Basically, phase space in most of the cases it is x and x dot, but here as it is represented as phase space with momentum, that means we have to write x and amx dot. It is not that much probability because only one a will be mathematical. That's it. Okay. Okay. So yeah. So we have to check that one. So how to do that? First of all, x of t we need to calculate. X of t is a cos omega t plus phi or minus phi, whatever. Okay. Then x dot I can write as a minus a omega sin omega t plus phi. Okay. Okay. Now they are asking x and x dot plane. So that means I can do one thing. I can square that x square as a square sine cos square omega t plus phi, and x dot square is a square omega square sine square omega t plus phi, right? So I can do one thing. X dot square divided by omega square is a square sine square omega t plus phi. Now you can understand a square cos square omega t plus phi plus a square sine square omega t plus phi can be written as a square. That means x square plus x dot square by omega square. So I can have x square plus x dot square by omega square as a square. Okay? So I can simply write here x square by a square plus x dot square by a square omega square equals to 1. Now I can do another thing as x square by a square plus x dot square multiplied by m a square m omega square equals to 1. So I can see this is nothing but an ellipse in the plane of x and m x dot, or it is like m square and here it is m square. Okay. So it is x square by a square plus mx dot whole square by a square m square omega square equals to 1. So it will be simply an ellipse like thing, depending on the value of a. So for this case, a is what? Capital A, because our ellipse equation is x square by a square plus y square by b square equals to 1. So our a square is capital S square, b square is a square m square omega square, a square m square omega square. So a will be a, b will be a m omega. Now the area is pi a b, that means pi a m omega. So it is pi m omega s square. Okay. Now we can see the options. But in the option, and the answer was pi m omega s square. But in that option, options it is given in terms of Vmax. So we need to calculate the Vmax as well. So how to calculate Vmax? We had H3 is this one. So H dot is what? Yes. So V of t is this. Now to get V as maximum, it should be maximum. So this whole should be maximum, means the sign has the maximum value as plus 1 or minus 1, plus 1 to minus 1. So if I write here plus 1, then it will give a minus sign. So that means we need the minus 1 here. So minus 1 sine, if sine omega t plus 5, I take minus 1, then it will come as a omega simply. So this is the Vmax value. So from there I can write here omega as Vmax divided by a. So if I am going to write here omega is Vmax divided by a, then what will happen? pi AB is pi A omega m A. This was my answer. Yes. So I can write pi A square omega m, which is pi A square V max by A m. So it is pi A V max m. So the answer will be m pi A V max. Now we can go for the option. We are getting pi m V max A. So this is correct as action number 2 A. These are all so here in this case what we have done, we have just calculated how x and m h dot will be vary in that phase space, and we found that it is indeed a ellipse equation, and if it is a ellipse equation then we can get semi-general axis. So from there I can have semi-general axis value A and B. Now the area is pi AB. So if I write this, then we need to calculate omega in terms of V max. To get that one, we need to calculate V, and then V max is A omega. So omega can be written as V max by A. So if I replace omega by V max by A, then by A, V max by A, M A. So it is like M by A V max. Okay. Now coming to question number 5. A harmonic oscillator of mass m1 has time period t. m1 has time period t. Basically, our harmonic oscillator is like that. Oscillator of mass m1 has time period t. If it is a m1, then time period is t. After mass m2 is added to the system, the new time period becomes what? Okay. Now in this case, it is like that. It is m1, it is m2. Now what will be the new time period? So previously when m is m1, t is what? First of all I need to check what is the omega value here. Omega square is k by m1. So omega is root over k by m1. Now time period t is 2 pi by omega. So 2 pi divided by m1 by k, right? So this is our old t. Now if I have new condition where our omega square is same k but m1 plus m2. So for this case omega is root over k by m1 plus m2. So for this case our t new is omega by 2 pi, then it is 2 pi by omega. So it is 2 pi by omega. So 2 pi root over m1 plus m2 divided by k. So if it is like that, then I can write like this, that 2 pi root over m1 by k plus m2 by k. Yes. I can also write it like, we already know that t is 2 pi root over m1 by k, and t new is 2 pi root over m1 by k plus m2 by k. So, can I write it like that? m1 by k 1 plus m2 by k into k by m1. Okay. So I can write it like 2 pi root over m1 by k 1 plus k will cancel out m2 by m1. Okay. So I can go here 2 pi root over m1 by k root over 1 plus m2 by m1. Now our t new will be that 2 pi root over m1 by k, this is coming as t, then 1 plus m2 by m1. Okay. So the answer is t into t new is t into root over 1 plus m2 by m1. Okay. Now you can see that this expression is correct. Also this expression is also correct. Why? Because if this is nothing but t root over m1 plus m2 by m1, so it is t into root over 1 plus m2 by m1. So this is also equal to this one. So both are correct here. So for this question what we have done, we just read like omega expression, then t expression, and we are done with the mathematics. Okay. So now coming to the next question. The differential equation for a damped harmonic oscillator is, okay, this is very simple question because we have already explained it in like Sir already explained in this lecture that what is the differential equation for a damped harmonic oscillator, and he also solved that one. So for damped harmonic oscillator, if damping is present here, that means some force which is proportional to the velocity. So I can write it like something, some lambda, 2 lambda and v. Or I can write 2 lambda x short. And as it is a decreasing one, because when that velocity will be increasing, the force will oppose the system. So that means it will be a minus sign. So now I have mx double dot, I have omega square x, I have also this. If I have all these things, then it will be simply, it should be t plus kx plus 2 lambda x dot equals to 0. So this will be x double dot plus k by m x plus 2 lambda by m x dot equals to 0. So x double dot plus omega 0 square. Why omega 0 square we are talking? Because lambda is also again a frequency like thing. Okay. So we will basically write it like omega 0, and later it will be omega square for the damping case. So I can write here as well one thing, that In the presence of damping, the binding energy rather decreases, energy is also decreases. So it will be simply this whole like okay, we should write it like that. Yes. So it will be come here. Yes. So it will be like this is in proportional to v, so that means something and then x dot. So something into x dot. So if I write here that something and x dot, then something x dot equals to 0. So plus something divided by m x dot equals to 0. So this whole that something divided by m, this one for our convenience of calculation we are taking as 2 lambda and then x dot. So I can have x double dot plus omega 0 square x plus 2 lambda x dot equals to 0. So this is the expression for damped harmonic oscillator. Now let me come here to the option. See, h double dot plus 2 lambda x dot plus omega square x equals to 0. Obviously, there it is not mentioning as x0 square, but that does not matter because omega square and omega 0 square, if I write, that is not a big problem. So basically, why we are writing here omega 0? Because that it is gamma. Sorry, and if the question is given as gamma, so that is also fine. We can write it as gamma as well. So let me write here gamma. Because this is just a constant, so that does not matter that what you are writing here as a constant. But the main important thing is that it should be function of x dot. That is the thing. Okay. So this is the case. And gamma has also the unit as omega. Like omega means like frequency. So that's why we are writing not going to write here this omega frequency. Okay. Now coming to the 7th question. Given initial conditions, what are the initial conditions? Initial conditions are at t equals to 0, x0 is x0 equals to 2. At t equals to 0, x dot t equals to x dot 0 equals to v of 0 is v0. So v0 is 0. Okay, v0 is 0. So the solution form best satisfies the simple harmonic motion equation. Okay. So the general equation for harmonic oscillator is xt is a cos omega t plus phi or minus phi, whatever. So now if I write here x dot t, this is like that, and 1 omega. Now the conditions are x0 is x0, which is 2. Yes. v0 is 0. So we had this. Now x0, I can write it a cos phi, which is 2. Now come here for x dot t. it is minus m a omega sine omega t plus phi. So x dot 0 is minus a omega sine phi. So v0 is given as 0. So minus a omega sine phi is 0. And omega a not equals to 0. That means phi is 90 degree. Sorry, phi is 0 degree. So that sine phi equals to 0. Okay, very good. Now come here. x0 is a cos phi equals to 2, and we got that phi equals to 0 degree. So if I write here cos 0 degree equals to 2. So a is 2 because cos 0 is 1. So our general simple harmonic oscillator equation is xt equals to a cos omega t plus phi 2 cos omega t. So this is the answer. So 2 cos omega t. 2 cos omega t is this one. So this is not correct, this is not correct, this is not correct. Okay? So what we have done here, we have taken the initial condition from the question and we write the solution and then apply the initial conditions to get the general solution. Now come to the question number 8. An external periodic force. External periodic force is Ft. The external periodic force Ft equals to F0 cos omega t. So F0 cos omega t acts on a mass spring system. Now when omega equals to omega 0, that means this is the natural frequency is omega 0 and omega is the frequency of that external force. So if omega equals to omega 0 means we are talking about the resonance condition, right? If this is the case, then the particular integral of motion increases with time. This happens because what? Okay, so to answer the question, first of all we need to check that whether in a forced harmonic oscillator the particular integral of the motion really increases with time or not. Okay, so to do that, what we can do, it is given that our forced oscillation means like forced harmonic oscillator means the external force is F0 cos omega t and the condition is given as omega equals to omega 0, where omega 0 is natural frequency. So for this case I can write the equation of motion as mx double dot plus kx equals to F0 cos omega t. So I can write again x double dot plus k by mx equals to F0 by m cos omega t. So this will be like x double dot omega 0 square x F0 by m cos omega t, right? Okay. Now, as we are talking about the resonance condition, so we can't write the trial solution of x as simply like a cos omega t, like alpha t plus beta or something like that, because we have seen that for omega equals to omega 0 it will blow up. So we have to take a particular type of trial solution so that we can have the resonance condition intact. Okay. So for this case, Sir has already explained this resonance condition calculation or the solution. So I am just going to do a little bit on that so that we can have a better feeling. Okay. So let me write another trial solution for that x. So I have, what is the thing I have? I have like this one. I have x double dot plus omega 0 square x equals to f0 by m cos omega t. If I have like that, then we will use, let's say I am writing here f0, then we will use the complex analysis, complex notation. So here I can have the expression of like okay, so if here this f t, I can write it f0 cos omega t, I can write it as the real of f0 e to the power I omega t. Okay, so I can write it real of f0 I omega t. Okay, fine. Now this is the complex amplitude of the forcing, like something e to the power I omega t. Okay. Now I can do one thing also to write the motion, equation of motion. I can also write d2y dt2 plus omega. Okay, this is omega 0 square. Okay, so let me write here omega 0 square. Omega 0 square equals to f0 by m e to the power I omega t. If I will write it, then we had d2x dt2 plus omega 0 square x equals to f0 by m cos omega t. So I can write from here to here by simply taking the real value. So the real of d2y dt2 plus omega 0 square y equals to real of f0 by m cos. Okay, so you can see that if I write here, just a minute. If I see here that if I write here f0 by m e to the power I omega t, that can be fine, no problem. But there will be another problem which we will see a little bit later. So what was the problem? The problem is like to find, so basically right now we need to find the yt. So for and then after that we can write, we can find the real of yt, and then we can have the value of xt. That is fine. But we will try the if I need to write y as simply e to the power I omega t and some constant, let's say m or something, then it will not gonna work. So for that case, what I need to write, y I can write it t, then e to the power I omega t, then let's say n. This I need to write. So why I need to write this one? Because it will blow up. So what y dot is t n I omega e to the power I omega t plus e to the power I omega t n. Now what is y double dot? It is okay. So it is like n I omega e to the power I omega t plus t n I omega e to the power I omega t plus n I omega e to the power I omega t. So the answer is like, you can see this is n I omega t, that means 2 n I omega e to the power I omega t, then there will be a minus, then omega square t n e to the power I omega t. Okay, so this is nothing but I can write it n e to the power I omega t common, then 2 I omega minus omega square t. Okay, so this is y double dot. Now y double dot is n e to the power I omega t 2 I omega minus omega square t. Okay, fine. Now I have this one and plus omega square y. So I can write it like n e to the power I omega t 2y omega minus omega square t plus omega 0 square n e to the power I omega t is equals to like f0 by m. Okay, f0 by m I think I have written somewhere something. Oh no, f0 by m is also like that only. So f0 by m e to the power I omega t. Okay, so now n e to the power I omega t 2 I omega minus omega square t plus omega 0 square, and okay, here t was there because it was y. So f0 by m e to the power I omega t. So e to the power I omega t will be cancelled out, and as omega is omega 0, we can see that omega is omega 0, that means these two will cancel out. That means we will only left with 2y omega is f0 by m. So n is f0 by m 2I omega. Now what is y right now? Y was t n e to the power I omega t. So I can write it t f0 by 2mi omega e to the power I omega t. So this will be like t f0 by 2m omega e to the power I omega t divided by I. Right? This is the thing. This is my y. Okay, fine. Now if this is my omega, this is my y, then what will be the real of y? So real of y is nothing but I can write it e to the cos omega t means e to the omega t means cos omega t plus I sin omega t whole divided by I. So it will be simply t f0 by 2m omega cos omega t by I plus sin omega t. So the real of y is nothing but t f0 divided by 2m omega sin omega t. This is my real of omega. Sorry, real of y. So that means our xt is t f0 by 2m omega sin omega t. So this is nothing but my pi. For pi we need to take the trial solution, so that's why we are just ending with this equation. So this is Pi. Okay. Now coming to the CF. Okay, no need to go for the CF, because in the question what they are mentioning that our xt is proportional to t directly. You can see obviously there is a term as t. I should not write like that. There is a term is which is t multiplied with f0 by 2 omega m omega sin omega t. So that means xt is proportional to t. That's what they are also telling in that question, that an external periodic force acts on a mass spring system when m equals to omega 0. Omega equals to omega 0, natural frequency, the particular integral of motion increases with time. That is correct. This happens because of what? Now we have, till up to this we already got the point, okay, that x pi is proportional to t. Now we need to check that why this is happening. This happens because of what? So for this case, I can write where I can write. So what I got x as xpi as t f0 by 2m omega sin omega t. Now I can write x dot of t as f0 by 2m omega sin omega t plus t f0 by 2m omega cos omega t and then 1 omega. I can write it like that. So it will be like 2m omega sin omega t plus t f0 cos omega t divided by 2m. Okay. So if I can write it like that, then I can also have the instantaneous power as P of t, which is f of t v of t. So this is nothing but v of t. So f of t I have in my question as f0 cos omega t, and then v of t is f0 by 2m omega sin omega t plus t omega cos omega t. Now you can see that this is f0 square by 2m omega, all the things will be outside, then cos omega t sin omega t plus t omega cos square omega t. So if I take the power average, then what I can get? I can get it like f0 square by 2m omega. This average will be 0, but here it will be simply half. So this one I can get. So P average I can get as f0 square by 2m omega t omega by 2. So P average I can have f0 square t by 4m. Okay. Now the energy average can be written as f0 square t square by 8m. So what does this mean? This means that the net positive work every cycle. So that means which absorbs energy continuously. The oscillator is absorbing energy continuously. These all things will not be correct. So for the explanation of this question, I just mentioned here, at the resonance, that means omega equals to omega 0 condition, the driving frequency matches the natural frequency, and the forcing term excites the natural mode in phase, such that the drive does net positive work each cycle. This is known as secular growth. In a real system, small damping limits the amplitude. Steady state resonance with finite amplitude occurs when input power equals to dissipative power. In the ideal undamped model, amplitude and energy grow without bound. So basically it is nothing but net positive work in every in every cycle. So which again indicates that it absorbs energy continuously. Okay, so this is the question. Now coming for the question number 9. Yes. So an oscillator of mass 0.2 kg is subjected to a periodic force 0.1 cos 5t plus pi by 4. What is the amplitude of steady state at t equals to 1? And the damping is negligible. And natural frequency is 5. That means omega 0 is 5 radian per second. Okay, so what are the things given here? You just need to write quickly. This is given. This is given. And it is. Here in this case, you can see this is a forced harmonic oscillator equation. So here I can write it like F0 cos, let's say, omega t plus beta, fine, and this is omega 0. But from this question, it can be F0 is 0.1 with proper unit, and omega is 5 radian per second, and beta is pi by 4. Now, if we just compare these two equations, omega is 5 and beta is pi by 4. Now you can see here that omega 0 is 5 radian per second. That means this is a condition of resonance. Okay, fine. Now what they are asking, damping is negligible. So that means in our calculation we will not consider damping. Okay. So, what is the amplitude of steady state? Okay, amplitude at t equals to 1. So, they need to know that this one. So, as it is a resonance condition, so the xpi at steady state. Steady state means we will just take the xpi case. So for this case, xpi, as we have already calculated that one in the last question, it is ft f0 by 2m omega. Let me write here same thing, t f0 by 2m omega. Then I think sine omega t. Sine omega t plus beta. So this is nothing but t is 1, f0 is 0.1, 2 into 0.2 into 5, then sine omega t plus beta. So for steady state current, the amplitude they are only asking, so that means this value we just need. So the value of this is like 0.1 divided by 2 into 0.2 into 5. So it is 1 divided by 20, so 0.05. So this is 0.05 meters. Why meter? Because it is given in the SI unit. So that's why. Okay. Now this one. A particle of mass m moves in a potential this If total energy is known, the turning points are given by, assume alpha is small and no significant effect of centrifugal potential term. Okay, all the things are given here. So I can simply write the total mechanical energy is half am h dot square plus v effective. So half am h dot square plus L square by 2m r square plus V of r. But in that assumption, they have taken that no significant effect of centrifugal potential term. That means this is coming as 0. So I can simply write this as this. Now V of r, or it is given in x, so half k x square plus alpha x to the power 4. So half m h dot square plus is x actually. This would be x. This is x. This is half kx square plus alpha x to the power 4. So our final E is this. Now at turning point, means what? Here r dot equals to 0. That means total energy is equals to the potential energy only. So I can write here E is simply half kx square plus alpha x to the power 4. So alpha x to the power 4 plus half kx square minus E is equals to 0. So from here they are basically want to know the value of x. So this is a second order differential equation of x square. So I can write it like alpha x square plus half kx square minus E is equals to 0. Now let's put y equals to x square. So it will be alpha y square plus half ky minus E equals to 0. So from there our y will be minus k minus k by 2 plus minus root over k square by 4 minus 4 a and b is minus 4 is by 2a by 2 alpha. So it is right here like that. So this is minus k by 4 alpha plus minus root over k square by 4 plus 4 alpha e whole divided by 4 alpha square. So this is minus k by 4 alpha plus minus root over, this is whole under root. Okay. So if I calculate this one, then k square by 16 alpha square plus 4 cancel out e by alpha. Okay. Now this is the solution for y. Now y is what? Y is x square. So that means we can take only the positive value, because if we are talking about x value, then obviously it will not come as a negative value. So for acceptable y, y is minus k by 4 alpha plus root over e by alpha plus k square by 16 alpha square. This is my y, acceptable y. Now what is x? X is plus minus root over y. Okay. One thing. I can do further modification is this. Here you can see I can write here 1 k square is common, then 16 alpha square is also common, then it will be like 1 plus e by alpha into 16 alpha square by k square, then minus k by 4 alpha, let me, yes, plus root over k square by 16 alpha square, 1 plus, you can see this is e, then into 16 into alpha divided by k square. So our y has minus k by 4 alpha plus k by 4 alpha root over 1 plus 16 e alpha by k square. Okay. So I can write it root y plus minus root y and this is x will be plus minus, you can see here, root over of whole thing minus k by 4 alpha plus k by 4 alpha into root over 1 plus 16 e alpha by k square. So I can do one thing from here, that root alpha means 1 by root over 4 alpha means 1 by 2 root alpha I can take out, and here it is minus k plus k into 1 plus 16 e alpha by k square. So I can write it minus k plus, as here it is mentioned somewhere that alpha is small quantity, alpha is small, so alpha is small means I can write it like k into 1 plus 16 e alpha by k square whole to the power half. So this one can be written as minus k plus k 1 plus 16 e alpha by 2 k square, as alpha is small. So I can have plus minus 1 by 2 root alpha root over minus k plus k into 1 plus 8 e alpha by k square. So it is like 2 root alpha minus k plus 8 e alpha by k. So this is 1 by 2 root alpha 8 e alpha by k. So it is plus minus 1 by 2 root alpha, this is 2 root 2 root e alpha by root k. Now you can see that root alpha will cancel out, 2 will cancel out, so root 2 root e by root k. So our x will be plus minus will also be there, plus minus root over 2e by k. So x is plus minus root over 2e by k. So this will not be there. Okay. So these are the things. Now I just want to go through for the whole questions. So this is, as I told, this is the previous week question number, week number 4, fifth question. Then the answer for this question is first one only. Trajectories are conic sections. So for this case, what we have done, please see that. Trajectory are conic sections, all the motions are bounded, that is not correct. Mechanical energy is always negative, that is also not correct. The trajectory is always circular, that is also not correct, because we have seen that the energies are always positive and all the motions are always unbounded, and there will be only parabola and hyperbola, these two options. Okay. Similar questions were there for question number 15, and obviously all three are coming as true. And they are asking that what will be the plot for effective potential versus R. So we were doing that one. Okay. Now this one, which is this year, this week question. 10 questions we were talking. So the first one is very simple, that M is given, K is given, they are asking for F. So we need to calculate the omega, then after that we need to calculate the F. And it is coming out like this. Then this one needs a little bit calculation. And it's turned out that A equals 2.828 as a Newton, phi equals 45 degree. How we did that? Xt as this one, then initial conditions are given, omega is also given, so amplitude they need to know, and phase we need to know. So xt, h dot t, then at t equals to 0, h0 equals to a cos phi, and they have given the x0 equals to 2 centimeter, so we will just put the value of x0, which is x at t equals to 0 as 2 centimeter. Then we will have the condition that a cos phi equals to 2 centimeter. Then x dot 0, this one we will also get as 3. Then we can see that I can have the omega value, tan phi value as 1, so phi will be 45 degree, and a cos phi equals to h0. From there I can have the value of a as well. So it is 2.82 and phi equals to 45 degree. Now this. This is coming as half kx square. How it is coming? Because we just need to write here half kr square. So xt is a cos omega t minus phi or plus phi, anything, it does not matter. So x dot t is, we will write simply this, and we will get this. Then omega square equals to k by m. We will convert omega square as k by m. So we will put all the things in terms of k and a. Then we are getting that equals to half kx square. So that means this one. Okay. The next question is this. Okay, the area of the ellipse traced by a harmonic oscillator phase space with momentum. 1 is there, then we just calculate x square and x short square. Then m square x short square, because they just need the calculation in terms of the phase space, x and momentum, so that's why. So this is the electric equation. From here I can get A and B value. Then area is pi AB, but the question option is given in terms of Vmax, so for that we need to calculate the Vmax also, and Vmax we can get from that Vt is this one. So as a whole the right hand side will be maximum with the sine omega t plus phi equals to minus 1. So Vmax is anyhow A omega. So from there omega is Vmax by A. So if I put the values pi A omega m A, then it is coming as Vmax by A. So m by A Vmax. So this is the answer. Then coming to the next question, this one we pictorially represent, and then we calculated the T new in terms of T old, and it is coming at like 2 pi, not 2 pi, T into root over 1 plus m2 by m1. Okay. Okay, then this is the case. After that we will have this question. This is very straightforward because I have already explained these things so many times, that what will be the differential equation for a damping harmonic oscillator. So this is the thing. I have in option number A. Okay, now this one has done. Here basically gamma we have just write as something that constant divided by m. So now coming to this question number 7. So this is the thing. Then if I write here x, so the answer will be coming as like x equals to 2 cos omega t. You can see that how we are doing that. Then okay, actually this is from the question number 8. The question number 8 is a little bit long. We just derived all the PI solution here, and then we get that okay, indeed the PI is a proportion function of, increases with the time because it is a function of T only. So how it is, why it is happening? This is happening the oscillator because the oscillator is absorbing energy continuously. So to know that answer, we just did that one, that x is given in this one, xPi, and x dot is this one. So V is this, then instantaneous power is Pt is Ft and Vt into Vt. So we just multiplied these two, then we are getting P average as this. So if P average is this, then we can have the energy average of this one, which is again the function of T square. So the oscillator is basically absorbing the energy continuously because T is directly proportional here. So it is taking the energy from the outside continuously. That's why our x the pi, the particular integral, is basically increases with time. Now we just calculated these things. And for the question number 9, this is also similar, that if the damping is negligible and natural frequency is also 5 radian per second, then what will be the steady state amplitude? So the condition is that one, and this is the amplitude part. So we have written that amplitude part here. This is the amplitude part. This is the XPI solution, XPIT. So then if I write here, then we will get the answer as 0.05. Now this. So for this case, what we have taken, these two assumption was there: alpha is small, centrifugal potential term has no significant effect. So this one will be 0, and Vx is given just like that. And then turning point, as turning point E equals to simply half k square plus alpha x to the power 4. Then we will just write all the terms, and we just simplify a little bit. Then y is this one, and y should be plus, to have the x square as real, not imaginary. So after that, after simplifying a little bit of y, then we are getting the value of x as root over plus minus root over y, and we are getting x equals to, very simply, it's a very simple result as plus minus root over 2e by k. So if I go for the option, it is like x equals to plus minus 2e by k. So this is the case. Okay. Yeah, so maybe we'll see the next class. Ta-da.